Hello everyone. So let's continue our discussion on generated clocks for divide by 2 circuit. So in the last video we came up with a relationship between this waveform and this waveform, and the relationship was divide by 2. So this was pretty straightforward because it was a binary division of the main clock period. This clock frequency. So the main clock frequency was just divided by 2 and you get this particular clock in this particular clock waveform. So is there any other relationship that we find between this master clock and this particular gen clock? So let's first, what we'll do is we'll first identify edges for this particular master clock. So let's say this is the first edge of the master clock, this is the second edge of the master clock, this third, fourth, fifth, and so on. So if you try to find a relationship between the edges of the master clock along with the generator clock, then can we do something about it? Okay, so let's try to identify that part. So for example, if you see this particular waveform, the rise edge of the generator clock starts at the first clock edge of the master clock. Okay, so the rise edge of the generator clock starts at the first edge of the master clock, and then after this rise edge, the next edge that comes for the generator clock is the fall edge, and the fall edge of this particular generated clock comes at the third edge of the master clock. So we are talking about the edges of the master clock. It could be rise, fall, anything. We are counting the number of edges of the master clock at which the generated clock edges comes. So if we start with rise comes at the first edge of the master clock. Next edge of the generated clock, which is the fall edge, comes at the third edge of the master clock, and the next edge, which is the rise edge, comes at the fifth edge of the master clock. This is one thing to observe. And second thing to observe is, if you are able to identify the rise edge, fall edge, and then the rise edge in this order, then this actually completes your waveform. This actually completes your generated clock waveform. So combining these two observations, can we derive some properties out of it? Okay, so the same generated clock properties which had got a divided by 2 option over here, what we'll do is we'll not use the divided by 2 thing over here. What we'll do is we'll be defining this particular property of the generated clock with respect to master clock. So it is in terms of edges. So it says 1, 3, 5. So what does this represent? It says that the generated clock first rising edge, okay, the generated clock rising edge arrives at the first edge of the master clock. The generated clock falling edge arrives at the third edge of the master clock, and the generated clock, the next rising edge, arrives at the fifth edge of the master clock. So any divided by 2s, any divided by n circuit can also be any clock waveform generated by the divided by binary division of the master clock can be represented by an edge option as well, or can be represented, the generated clock properties can be derived with the help of the edge thing. Okay, but the reverse is not always true. For example, if there is some edge, if there is a waveform that can be defined only by its edge characteristics, it can't be defined by its divided by 2 characteristics. So vice versa is not true. But anything which is defined, any generated clock which is a binary division of the master clock, can always be represented by an edge option. So let's look into another example. For example, we have a divide by 3 circuit. Okay, so divided by 3 circuit, the waveform, so for example, we have this black box, where this black box receives an input of the master clock, and the output of this particular black box is nothing but a generated clock, which is a divided by 3 clock. Okay, so let's say this is the master clock. We'll take the same waveform that we had before. This is the master clock, and if we say a divided by 3, it means that 3 clock cycles represent 1 clock cycle at the output. Okay, so this is 1 clock cycle, this is 2 clock cycle, this is 3 clock cycle. So 3 clock cycle at the input, will now determine one clock cycle at the input. So basically the output clock period is a multiple of the master clock by 3, something like this. Okay, but in this case, one thing to observe is, first, the duty cycle is not 50%. In this case, the duty cycle is, for example, duty cycle is from this point for what amount of time your clock remains at the rise edge, and for what amount of time your clock remains at the fall edge. In this case, the duty percent is 33 and 66% in that range. So the rise edge is the clock pulse is at the rise edge for 66.666%, and the clock edge is at the fall side for remaining 33.33%. Okay, so duty cycle is not exactly 50%. So this waveform, and the second thing to observe is, this waveform has got certain relationship with the master clock in terms of edges. So in this case, the rise edge of the generated clock comes at the first clock edge of the master clock. The second fall edge of the generated clock comes at the fifth clock edge of the master clock, and the third rise edge of the generated clock is coming at the seventh edge of the master clock. So how will this particular thing will filling up this particular table it's something like this. So you have the generated clock, the name of the generated clock, let's call it gen underscore clock. The source name or the port name is the master clock, and these are the edges of the generated clock which defines the generated clock. So it says that the gen clock arrives at the rise edge of the gen clock. The first rise edge of the gen clock arrives at the first edge of the master clock. The second fall edge, the first fall edge of the gen clock arrives at the fifth edge of the master clock, and the second rise edge of the gen clock arrives at the seventh edge of the master clock. So this particular feature of generated clock completely defines the generated clock relationship with the master clock. Okay, so in this case, this can't be substituted by a divide by option, and the reason is this is not a 50% duty cycle. Okay, had it been something like this, the switching would have been something at this particular clock period, it could have been defined by a binary division, by a divided by 2, but in this case it can't be. Any binary division of divide by 2 can be represented by an edge. Any binary division at the edge can be represented by a divide by 2, but the waveform which is of this kind can't be even though it's a dividable circuit, but it can't be represented by a dividable circuit. Okay, so that's the problem that we see with the edge option and the divide by 2 option. But we always have a secondary option that will help to model the gen clock waveform in terms of master clock. So basically this is all about finding a relationship of the gen clock with the master clock, and these are the options that are available with the designer. So using these options, using all of them or some of them of this particular options, we need to find out a way how the gen clock can be related to the master clock. Okay, so now what we'll do is we'll look into another circuit. It's called divided by 2 inverted circuit. So the waveform looks something like this. So for example, initially you had this master clock and the gen clock was a divided by 2 of the master clock. So what if I just put an inverter over here? Let's say I put an inverter over here. The waveform shape gets inverted. It's still a divided by 2 of the master, but the waveform shape gets inverted. Okay, so this is how it will look like. You have the master clock, your gen clock is an inverted form of the master clock. Okay, it's a divided by 2 inverted form of the master clock. So how do we represent this kind of waveform? So the best way is to do by edges. So first let's represent the gen clock and give the name as gen underscore clock, give the source name as master underscore clock. Okay, and either you can use a divide by 2 option and use an inverted. You just use the inverted options over here. So this particular thing represents a gen clock with an inverted characteristics, and the remaining will be cross. So these are remaining are not used. Or what you can do is, there is one more way. You can avoid the divide by option, and you can give edges option. You can give 3, 5, 7. So 3 is the first edge of the gen clock, or the first rise edge of the gen clock. It says that the rise edge of the gen clock arrives, the first rise edge of the gen clock arrives at the third edge of the master clock. The fall edge of the gen clock arrives at the fifth edge of the master clock, and the next rise edge of the gen clock arrives at the seventh edge of the master clock. So this will represent your waveform, and the inverted relationship between these two will be still obtained by the inverted options that we have over here. Okay, so this is how the inverted option is being used in to define the relationship between the gen clock and the master clock. So what we'll do is, since we have learned about edge, we have learned about the edge characteristics of the gen clock, we have learned about the divide by characteristics of the gen clock, we have learned about the inverted characteristics of the gen clock. What we'll do is, we'll derive a waveform. We'll have a waveform generated over here, and we'll try to derive the properties over here. Okay, oh sorry, the other way around. We'll be giving you the properties over here, and we'll try to derive the waveform out of this particular properties. So let's try to do this in the next video. Thank you.